So just to repeat, type of forces so far we have is normal force. It's perpendicular from surface. When is it present? At surfaces, symbol Fn. And here's our basic equation for normal force is equal to the force of gravity. Now, that's the basic equation for in this case. When we start dealing with objects on inclined planes, ramps and stuff, the equation is going to slightly change. It's going to be a part of gravity that the normal force is going to be equal to. But that comes later. And again, a force is an interaction between two or more objects. Okay. Friction, always opposite an object's motion, present at surfaces through the air, symbol F sub F. Or you can say, over time, you just say just F for friction force. The equations, there's two types of friction. We're going to deal with that down the line, but to just throw them up here. There is static friction. You know when you're trying to push something and it just won't budge, continue, you're just trying to push it, the static friction is opposing you. And you have to push so hard to overcome the force of static friction to get it moving under another type of friction called kinetic friction, because that's going to be the friction of movement. But before it starts going, static friction. It's just you're trying to push it, and it won't do anything, it won't budge. So that's static. The equation mu, take my word for it for now. We'll be extrapolating these soon. Mu sub s times the normal force. Basically what mu s is that it's the property of friction that exists between the object that you're trying to push or pull and the surface that it lies on. So coefficient of static friction, how much friction does that surface and that object have? Wood on wood, concrete on rubber, all these different interactions have different coefficients of friction. They have different types of friction. And then there's the little guy here, smaller than static friction. It's the kinetic friction, mu k Fn. Just writing the equations now. You don't have to understand the rudiments now. We will as we take care of friction. Those are basic equations for friction, static friction, kinetic friction. Another type of force, gravitational force. Right? And the gravitational force is always going to be towards the center of the mass in question. Keep things simple. We're not going to talk about universal gravity yet, but we're going to talk about the Earth for right now. So the gravitational force is going to be always towards the center of the Earth. Center of any mass, really, but we're on the Earth for right now. Always towards center of mass. Yeah. I don't not want to write that because we're going to go from Earth soon, and so we won't just talk about Earth. Oh, gravity only exists on Earth. No, always towards the center of mass. So center of mass and center of gravity are really the same thing. When is it present? All the time. In any gravitational field, aka all the time, you can never get a place of zero gravity, like where the gravity does not exist. The space-time metric in the universe, for example, there are just basically no holes for it. It's just a huge sheet, big geometric sheet of gravity or space-time. So there doesn't seem to be any holes, but gravity is in any gravitational field. It's kind of funny to imagine a flat earther physicist trying to reconcile gravity and everything. Yeah, it's pretty ludicrous. Yeah. I mean, explain the moon phases, but that's one of many things. Symbol F sub g for force of gravity. And the equations are various. So we're going to talk about the universal force of gravity. We're going to talk about gravity in different contexts of our chapter 5. But our basic equation that the force of gravity is going to be equal to mass times gravity, which is a form of mass times acceleration, which is Newton's second law. What I'm saying here, Fg equals mg, this is equation for weight. When you stand on a weight scale, that scale is measuring your mg. It's measuring how much matter you have and multiplying it by gravity, or not, real-time calculation, but it's measuring this mg, which is your weight. And that comes down type 12. Another type of force, tension. Okay, that's going to be relevant to the things that we're talking about in chapter 5. And the tension force is going to always point, or it always points away from objects. So if I have a sign that's hanging by two wires or something, the tension force is always going to go towards the ceiling, okay, away from the object. And we'll be diagramming all that. When is it present? Well, in strings, ropes, and the like, right? So things that just provide tension. Wires. Expression for tension force, F sub T. And we'll be seeing that we can just use this T for tension force. Bridges, yes. That's more or less of normal force. There's tensile strength of bridges, like if you were talking about like how they're going to bend and pull and stuff like that, Young's modulus, but not like in the tension I'm thinking about right now. Yeah. There's no real like one equation for tension. It's going to be taking many forms, so it's not available. I mean, it's going to be what it's going to be in different contexts. There is the spring force. And this direction is parallel or anti-parallel to motion. So for example, if you can imagine, but if you can imagine a mass on a spring, get a mass, attach it to a spring, and attach it to like the ceiling or something, and you pull down on that mass, the spring force is going to go against the mass. As the mass goes down, the spring force goes up. As the mass goes up, the spring force goes down. It's always against the motion. Okay, parallel or anti-parallel to the motion. So I should say realistically, in that example, spring force is always anti-parallel, right? Because if it's always going against you, it's anti-parallel. And we'll deal with that when we get to spring force. We'll talk about how the spring force is also known as a restoring force, because the spring force is trying to restore the system back to zero. It started off at zero, spring force is trying to get it back. It's always going against you. You're moving one way, I want to oppose you. I want to come back. I want to restore the system. When is it present? In springs, rubber bands, all springy things, elastic things. Elastic stuff. And the symbol for spring force, F sub S. And the equation Fs equals negative Kx. Don't worry about that too much here, but the K is called the spring constant. That's basically how strong your spring is. Some springs are stronger than the other. And X will be the displacement from zero. How far does your mass move from equilibrium, from zero? We also have the magnetic force. Are these all the forces? No. Types. The magnetic force is going to be perpendicular to both magnetic fields and charge velocity. B for magnetic field, that's the symbol for magnetic field. And I'm going to abbreviate velocity of a charge. So imagine a proton moving in a magnetic field pointing up or down, whatever. The magnetic force is going to be perpendicular to both of those directions. So we have a three-dimensional deal going on here. The magnetic force is in any magnetic field, because like the gravitational force is in any gravitational field, the magnetic force is in any magnetic field, and the electric force is going to be in any electric field. The fields are important. That's why we call these forces field forces, because without the field, you're not having a force. Right? And the fields have energy too, so all that stuff comes before any type of forces interaction. This symbol for magnetic force is F sub B, and the basic equation for magnetic force equals Q V cross B. And we'll be dealing with this cross symbol. It's going to be different from dot symbol. There are two types of multiplication. In this situation, when you cross two vectors, like a velocity and a magnetic field, you're going to get a new vector of magnetic force. So first of all, and that's what happens with torque. That's what happens with angular momentum. That, we'll be seeing that. We'll be dealing with torque. We'll be dealing with angular momentum. Not so much magnetic force. Only if we were doing the E&M part.
Could you read the equation again, please?
Yes, this is F sub B as in boy equals Q, V as in Victor, cross or X multiplied by magnetic field. Q stands for charge, electric charge. Protons and electrons have the same charge. We just call one negative, positive. And the direction of the magnetic force for a proton is different than an electron. If you've ever seen in particle physics, or if you've ever seen like these little spiral arrays of particles, like there's some particles that are spinning to the left and some particles spinning to the right. By knowing the orientation, by knowing the direction of magnetic field, you can tell which one is a proton and which one is an electron by their spin. But that's for later. All right, we won't fill this in, but we'll just talk about Newton's first law, okay? Because that's, we intimated at it, we hinted at it here. And so basically, what is Newton's first law? This deals with section 5.1, 2, and all that. An object at rest remains at rest, or constant velocity, because a lot of times they say, oh, it stays in motion. Well, let's be a little bit more, technical and specific about it. it stays at rest or it stays in constant velocity unless acted on by an outside or external net force. So the constant velocity part, we know that from CVPM. We've seen CAPM. Now we're into BFPM, balanced force particle model. We're now starting to talk about the causes of the motion by any force, by any interaction between two or more objects can accelerate the object. Or if the forces are balanced, that means if they're equal to each other in all directions, then the object remains at rest or it stays at constant velocity. And so I will be expounding on that in a bit. Newton's third law. For every action, there is an equal and opposite reaction. And like you place your foot on the ground, force of foot on ground is equal and opposite to the ground on foot. Let's say F1. So let's call this two objects, right? Force of object 1 on 2, as we denote it like this, is going to be equal and opposite of 2 on 1. Whatever 1 and 2 are, that's your basic idea. But it's one object that's going to be seen to move the most, the one with less mass. You put all your weight on the ground, and then you even put more by you compressing your legs. You're going to be the one seen accelerating because you're considerably less massive than the mass of the Earth. Even though the forces are the same, equal and opposite, it's the one with less mass that moves. The Earth moves too, but it's so indetectable. Like it's basically zero. There's accelerations from both objects. If you're on ice skates and you're with a friend and you guys are basically the same mass and you push off each other, the one with slightly more mass is not going to move as much as the one with less mass. So that idea. I'm not going to get to this too much today, but next time. Well, I was talking about Newton's first law, but here's the idea. Newton's first law is basically a law of equilibrium, balance. Things stayed the same, constant velocity, at rest. So basically, there are two conditions of equilibrium. You can be at rest or constant motion, constant velocity. That's where we've come from. We've come from the CVPM world. Constant acceleration, now forces, the causes of these motions. The reason of the kinematics equations, the forces involved. And the equation or relationship for these conditions of equilibrium, these only exist when the total number of forces or the net force is equal to 0. Okay, so Newton's first law, like law of balance. We have Newton's second law there, but we can remember this, the last part of Newton's first law, unless acted on by an outside net force. Once that net force comes in and disturbs the balance that was once there, now have a situation where that outside force that's bigger than everybody else is going to accelerate. okay, is going to accelerate the mass in question or masses. So this is Newton's second law in a nutshell. F net equals mass times acceleration. And good question. Yes, you may. So your book, I think, will talk about the Newton's second law as this way. So acceleration is equal to net force divided by mass. You're just solving for acceleration. And then they'll say some nice stuff like, okay, the acceleration is directly proportional to the net force and inversely proportional to the mass. Yeah, that's too wordy. But yeah, that's what we have. So like I was saying before with Newton's third law, both objects will accelerate, but the one with less mass is going to accelerate more. The force being the same, force being constant between both. By this definition, since acceleration is a vector and force is a vector, would mass be a scalar? Yes, it would be. Totally. As we can see there. And as I was saying before, like when you have a scalar times a vector, you get a new vector. You know, the scalar is just chilling, just staying there. There's still a pointing. You know, something's pointing some direction. But the product is a new vector. And likewise, if something more massive under the same force, the acceleration is very small. The Earth considerably is what 10 to the 24th kilograms. I mean, you're not going to accelerate the Earth under 2 newtons of force. Not to any degree. You need 10 to the 30th newtons or some sort of huge comet or some large force to come in. So that's Newton's first and second, and Newton's third. Again, every reaction, equal opposite reaction, we have force of 1 on 2, opposite force of 2 on 1. So let's say that object 1 is your foot, and 2 is Earth, as mentioned. So we can just say F of F on E is equal to equal and opposite E on foot. That's what's going on. And your 2 objects can be any 2 objects. Newton's third law always involves 2 objects. Yep. And so that will end it for today. The first part of this packet. We'll talk about this stuff, FBDs, free body diagrams, and system schemas next time. And we'll get into worksheet 1. Okay, so there's that.